In this first topic is sequences and series. First, we can define what is the definition of the sequence. Sequence is nothing but a mapping S from Z plus to R is called a sequence of real numbers, and it is denoted by Sn in curly brackets. For example, Sn is equal to 1, 2, 3, so on. And we can take Sn is equal to the natural number set. Okay, that is the sequence Sn is equal to natural number set. The natural number set having the set of 1, 2, 3, so on. Okay. Definition means a sequence Sn or a mapping Sn or a function S from Z plus to R is called a sequence of real numbers and it is denoted by Sn. For example, we can take S is a mapping in that Z plus means here n equal to 1, 2, 3, so on. We can take S1, S2, S3. These are the terms of the sequence. And those terms are having the any real values. That is into capital R means the values are belongs to capital R set. So such the mapping is said to be the sequence of the real numbers, and this is denoted by the sequence Sn. Here sequence Sn is nothing but it is the summation of S1 comma S2, not summation. That is the sequence of the S1 comma S2 comma S3, so on, this one. Here, what is the difference? Difference is the S2 minus S1. The difference will be the common difference is there. Here we can take the first S1 is equal to 1, S2 equal to 2, S3 equal to 3, like this in this example of the sequence Sn. Here S1 equal to 1 means this one, the values are 1, 2, 3, so on. And we can take one more example also. Sequence Sn is equal to minus 1 whole power n for all n belongs to Z plus. In this, you can take S1 equal to minus 1, S2 equal to 1, S3 equal to minus 1, S4 equal to 1, like this. This is the one type of the sequence. Okay. This is the definition of the sequence. Here, what they are taking here, Z plus. Z plus means we can take the N1, N2, N3, N4 values and associating with the terms of the sequence Sn. Those terms are belongs to R means we know that the natural number set is subset of whole number set is subset of integer set of rational is subset of real number set. So we can take any value that is the higher set is the real number set. So here the mapping is defined from Z plus to R means the value is whatever the value. We can take Sn is equal to 1 by x for x belongs to capital N or Z plus. Okay, that is the relation. Or we can take, if it is Z plus, then we can use the values. Or we can take the Z means we can take negative values or positive values. That depends on the define of the sequence only. But the definition of the sequence is a mapping from Z plus to capital R. Okay. Next definition is the bounded below definition. Bounded below bounded above, and bounded. Bounded below means a sequence Sn is said to be bounded below if there exists some real value k1 belongs to capital R such that k1 is less than or equal to Sn, where k1 is called bounded below. If sequence Sn, for example, we are taking Sn is equal to n for all n belongs to Z plus, suppose we are taking. Here Sn equal to 1 means the sequence Sn equal to set of the all terms 1, 2, 3, so on. Indirectly we can take the example of the natural numbers. The natural number set having lower bound. Lower bound means it has the minimum value 1, 2, 3, but there is no maximum value. Okay. So here what is the minimum? K1 is the minimum. That is nothing but 1 is the minimum for all the terms of natural number set. In the same way, here k1 is equal to 1, 1 is less than or equal to Sn for all n belongs to Z plus, that is nothing but we can take S1 is 1, S2 is 2, S3 is 3, S4 is 4, so on. Okay, this is the best example. We can take the whole number set is also bounded below set only, bounded below sequence, whole number set. The whole number set is starts with 0, 0, 1, 2, 3. So the lower bound of the whole number set is equal to 0. 0 is the lower bound or bounded below. What is the definition? A sequence Sn is said to be bounded below if there exists k, any value belongs to capital R such that k1 is less than or equal to Sn, where k1 is called the bounded below. The best examples are the natural number set and whole number set or the bounded below sets. Or the collection of the natural number set is the bounded below of the sequence Sn. The collection of the whole number set elements is the bounded below set element, whatever it may be. The next definition is the bounded above. Bounded above means a sequence Sn is said to be bounded above if there exists K2 belongs to capital R such that Sn is less than or equal to K2, where K2 is said to be bounded above. The best example is Sn is equal to 1 by n for all n belongs to Z plus. Here we can take S1 equal to 1 by 1 equal to 1, S2 equal to 1 by 2 is 0.5, S3 equal to 1 by 3, it is equal to 0.333. S4 equal to 1 by 4, it is equal to 0.25, so on. Here observing all, the S1 has bounded above, that is nothing but Sn is less than or equal to K2. That is the comparing the all values 0 point where K2 is equal to 1. So here 1 is the bounded above of the sequence Sn. Okay.
Yes,
We
ma'am.
can we can take another example also. Second one, Sn is equal to 1 by n square. Third example, Sn equal to 1 by n cube for all n belongs to Z plus. These all are having the bounded above element, but the other taking n or the increasing, the sequence values are decreasing. Okay, this is the bounded above. Bounded above means the sequence has upper bound, it has upper bound. So here the Sn is the one, the values are goes to reaches to 0. Why? Because 1 by infinity it goes to 0. So lower bound is 0, but here it is exactly the bounded above the value. Okay,
Yes, ma'am.
it has the bounded above when n belongs to 1 by n, where n belongs to Z plus. Next definition is bounded sequence. A sequence Sn is said to be bounded sequence if there exists K1 comma K2 belongs to capital R such that K1 is less than or equal, K1 is less than, Sn is less than K2, or K1 is less than or equal to, Sn is less than or equal to K2. Not less than or equal to, K1 is less than or equal to, Sn is less than or equal to K2, where K1 is lower bound, that is nothing but bounded below, and K2 is upper bound, that is nothing but bounded above. For this, the example is Sn is equal to set of Sn equal to minus 1 whole power n for all n belongs to Z plus. One example, the second example, Sn equal to minus 1 whole power n plus 1 for all n belongs to Z plus. Here, suppose we can substitute n equal to 1, 2, 3, then S1 is equal to minus 1, S2 equal to 1, S3 equal to minus 1, S4 equal to 1. So it has minus 1 is less than or equal to, Sn is less than or equal to plus 1. Here K1 is equal to minus 1, K2 equal to plus 1. This K2 is the bounded above, K1 is the bounded below. Least upper bound, we can, that is nothing but it is the another definition. Least upper bound is the bounded below or lower bound. It is the bounded above. It is the upper bound. Okay. Here in the second one, we can take minus 1 whole power 1 is minus 1 plus 1, it is equal to 0. So S1 equal to 0. S2 equal to minus 1 whole square is plus 1 plus 1, it is 2. S3 equal to 0. S4 equal to 2. So here also 0 is lower bound, 2 is the upper bound. So the each and every sequence values are either equal to 0 or equal to 2. So here it is K1, it is K2. Okay. Next definition, monotonically increasing sequence, monotonically decreasing sequence, monotonic sequence. First one is monotonically increasing sequence. Here, monotonically increasing sequence is nothing but a sequence Sn is said to be monotonically increasing sequence if Sn is less than or equal to Sn plus 1. That is nothing but S1 is less than or equal to S2 is less than or equal to S3 is less than or equal to S4, so on. The example of monotonically increasing sequence is Sn equal to n for all n belongs to Z plus. Sequence Sn equal to n. Here we can take S1 equal to 1, S2 equal to 2, S3 equal to 3, so on. And here 1 is less than, 2 is less than, 3 is less than, so on. So the relation is satisfies. But we can take minus 1 whole power n is there. It is not monotonically increasing. Why? Because in this, the alternate values are coming minus 1, 1, minus 1, 1. But it does not satisfy the relation of S1 is less than or equal to S2. So this is the not an example. So what is the difference of the monotonically increasing and monotonically decreasing means? For each and every value, the relation satisfies Sn is less than or equal to Sn plus 1. The second definition is monotonically decreasing sequence. Monotonically decreasing sequence means a sequence Sn is said to be monotonically decreasing sequence if Sn is greater than or equal to Sn plus 1. Example, sequence Sn equal to set of 1 by n such that for all n belongs to Z plus. This is here S1 equal to 1, S2 equal to 1 by 2, S3 equal to 1 by 3, so on. In this, we get the relation S1 is greater than, S2 is greater than, S3 is greater than, so on. So it is called as the monotonically decreasing sequence. Okay.
Yes, ma'am. Understood.
Third one in this monotonic sequence. A sequence Sn is said to be monotonic sequence if it is either monotonically increasing or monotonically decreasing. If it is either decreasing or increasing, either monotonically increasing